Department of Collegiate Education, Digital Learning, BSc 3rd semester, Physics 301, Electricity and Magnetism, DC Circuit Analysis. This video is presented by Savita S. So the contents of the video are overview, statement of superposition theorem, proof of the theorem, explanation with a solved example. So in this video, we'll be discussing about superposition theorem and its application. Superposition theorem is applicable to complex networks having several input sources. Sources in the sense here, batteries. It is derived from superposition principle and applicable to linear systems. Superposition principle states that the net response caused by two or more stimuli is the sum of the responses that would have been caused by each stimulus individually. If input A produces a response X and input B produces a response Y, then input A plus B produces a response X plus Y. So when both the inputs are present, A and B, the response will be X plus Y. If only A is present, it is X. If only B is present, it is Y. And when both A and B are present, it is X plus Y. The same principle is applied to superposition theorem. So this superposition theorem helps in simplifying the circuit analysis. So the statement of the theorem is as follows. In a network with two or more sources, the current or voltage for any component is the algebraic sum of the effects produced by each source acting separately. Method consists in removing all sources except one. Current and voltage across the required resistor is calculated. The process is repeated for all other sources taken one at a time. Finally, the algebraic sum of I and V across a resistor due to different sources is taken. So here we have a network having two sources, E1 and E2. So the method involves taking one source at a time. So we have to take only E1 at a time with the remaining passive elements as it is and find the currents at different branches, current through different branches, I1 dash, I2 dash, I3 dash. Again, remove the first source, take the second source, find the currents at different branches, I1 double dash, I2 double dash, I3 double dash. So the net current is calculated. Net current is calculated by taking the algebraic sum of current through different branches. So I1 dash plus I1 double dash, I2 dash plus I2 double dash, I3 dash plus I3 double dash. So the sum of all the algebraic sum of the currents of the two circuits will give the current when both the sources are present. So that is what the theorem says. So we will see whether it mathematically is it true or not by applying KVL to the loops of the diagrams. So first we'll consider the first diagram A. So applying KVL to loop 1 of diagram A. KVL means Kirchhoff's voltage law. So we have to apply Kirchhoff's voltage law to diagram A, loop 1 of diagram A. So in loop 1, we have taken clockwise direction as positive. So you can see the arrow here. Arrow says that the assumed direction here is clockwise direction as positive. So according to KVL, sigma E is equal to sigma IR. Sigma E means sum of the sources. So there is only one source in this loop. So E1, sigma E is E1 is equal to sigma IR, the IR products. So IR products are I1 R1 plus I3 R3. In this loop we have only two branches, R1 and R3. So I1 R1 plus I3 R3. I3 is nothing but I3 is I1 plus I2. I1 is the current entering the node. I2 is the current entering the node. I3 is the current leaving the node. So according to KCL, for this network, if you apply KCL to this network, I1 plus I2 is equal to I3. So instead of writing I3, we can write I1 plus I2. This branch is common to both loop 1 and loop 2. So I1 will also be flowing across R3, through R3 and I2 will also be flowing through R3. So I3 is I1 plus I2. So instead of writing I3, we can write I1 R3 plus I2 R3. So that is equation 1. So similarly apply KVL to loop 2. If you apply KVL to loop 2, In the second loop we have source E2. So sigma E is E2 and sigma IR. Sigma IR is I2R2 plus I3R3. Here we have taken anti-clockwise direction as positive because the currents are all flowing in the anti-clockwise direction. So we can take any one direction as positive, either clockwise or anti-clockwise. So if you apply KVL to loop 2, then E2 is equal to I2R2 plus I3R3. Again I3 is written as I1 plus I2. That is equation 2. Now we'll come to diagram B. So we take one source at a time now and apply KVL to both the loops. So for the first loop, E1 is equal to, now as we have only one source, current will change. Current through different branches will change. We don't have the second source. So let the currents are I1 dash, I2 dash, I3 dash. So if you apply KCL, Kirchhoff's current law, to this network, I1 dash plus I2 dash is I3 dash. Current entering the node is equal to current leaving the node. I1 dash plus I2 dash is I3 dash. So instead of I3 dash, we can write I1 dash plus I2 dash. So for the loop 1, if we apply KVL, I1 dash R1 plus I1 dash R3 plus I2 dash R3 is equal to E1. That is equation 3. And for the second loop, there is no source, so sigma E is 0. 0 is equal to I2 dash R2. Again, anti-clockwise direction we have taken as positive. I2 dash R2, I3 dash R3. I3 dash is again I1 dash plus I2 dash. So that forms equation 4. So we have applied KVL to diagram A and diagram B. Now apply KVL to diagram C. So applying KVL to loop 1 of diagram C. Here we have the sources. We have removed the first source and retained the second source. So E2 is equal to. So again the currents will change. Now the battery has changed. So the currents will change. I2 double dash, I1 double dash, I3 double dash are the different currents in the branches. So E2 is equal to I2 double dash R2 plus I3 double dash R3. So for this network, if you apply KCL, I1 double dash plus I2 double dash is I3 double dash. So instead of writing I3 double dash, we can write I2 double dash plus I1 double dash. So applying KVL to loop 2 of diagram C, so 0, there is no source here, 0 is equal to I1 double dash R1 plus I3 double dash R3. Again I3 double dash is I1 double dash plus I2 double dash. We get equation 6. So we got 6 equations, 1, 2, 3, 4, 5, 6 by applying KVL to different loops of the diagram A, B, C. Now adding equation 3 and 6, we get E1 is equal to, equation 3 is E1, equation for E1, and equation 6 is 0 is equal to I1 double dash R1 I1 double dash R3 I1 double dash. So if you add, you will get on the left hand side E1. The E1 plus 0 is E1. On the right hand side we get this. If you compare this with equation 1, because in equation 1 also we have E1. So if the left hand sides are equal, right hand sides also should be equal. So wherever we have I1, we have I1 dash plus I1 double dash. Wherever we have I2, we have I2 dash plus I2 double dash. So we can write that I1 is equal to, if you compare equation 7 with 1, left hand sides are equal, E1, right hand sides are also equal. So R1, the coefficient of R1 in equation 1 is I1. Coefficient of R1 in equation 7 is I1 dash plus I1 double dash. Similarly, coefficient of R3 in equation 1 is I2. Coefficient of R3 in equation 7 is I2 dash plus I2 double dash. So they are equal. Similarly, we can add 4 and 5 to get equation 8. And comparing 8 and 2, we get a similar kind of result. Hence, superposition theorem is proved. So if you take I1 dash is the current that you get when you have single source E1. I1 double dash is the current when we have second source. So I1 is the current when both the sources are there. So I1 dash plus I1 double dash is I1. Similarly, I2 dash is the current when E1 is there. I2 double dash is the current when E2 is there. I2 is the current when both the sources are there. So I2 is equal to I2 dash plus I2 double dash. Explanation with a numerical example. So we have taken a circuit where the battery voltages are known, resistances are known, only unknowns are currents and voltages. So we have to find current through different branches and voltages across different resistors. So the method involves taking one source at a time. So you take 10 volts and find what are the currents, and take 5 volts and find what are the currents. Then add the currents to get the total current. So if you take only 10 volts at a time, find the currents. So how to find the current? So find the main current. So to find the main current, we need to know the effective resistance. Effective resistance is, there are three resistances here, 100, 5 and 1K. 5K and 1K are in parallel combination. That parallel combination is in series with 100. So 100 plus 5K into 1K divided by 5K plus 1K. That is effective resistance is 933. So main current I1 is equal to E by R. E is the EMF of the battery. R is the effective resistance. So 10 divided by 9, 10.7 milliamps is the main current. So we'll find the branch currents I2 and I3. Branch current is given by branch current formula. Branch current is main current into resistance of the other branch divided by sum of the resistances. Suppose this is R1, R2 and R3. Then branch current method says main current into resistance of the other branch divided by sum of the resistance. Suppose I want I2. Then main current is 10.7. Resistance of the other branch is 1K divided by sum of the resistance. 5K plus 1K is 6K. So similarly find I3, branch current by branch current method. So for the second circuit also, we do the similar set of calculation. So we take 5 volt only, single battery, by removing the first source. We take the second source now. Find the effective resistance. So the main current is now I3. Branch currents are I1 and I2. So the effective resistance is 100 plus 5K are in parallel combination, and that combination is in series with 1K. So 1K plus 5000 into 100 divided by 5000 plus 100 is this much effective resistance. So I3 is equal to E by R. So E is 5 volts here. Effective resistance is 1098. You get this much. So I2 and I1 are the branch currents that we calculate by branch current formula. So I2 is the main current into resistance of the other branch 100 divided by sum of the resistances. Similarly find I1. So total current through 5K, let us say if you want the total current through 5K when both the sources are there, then add the current from the first this figure 2, and add the current from figure 3. So you get 1.87 milliamps. So voltage is total current into total resistance, that is 9.35 volts. So by finding individual currents, we take the algebraic sum of the currents and calculate the net current. This current is when both the sources are present. This is the current that we get when both the sources are present. So for future references and further studies, you can refer the following references. Thank you.